We do these seminars every second Wednesday of the month, except in the summer period. And I think we've been running for a couple of years already. And this time it is my pleasure to introduce Professor Niels Nørmark Sørensen, who has since 1991 developed and used computational fluid dynamics on many problems, including wind turbines, terrain, among those famous Bolon Hill experiment, even buildings or bluff bodies. He has really been into the basic developments of methods for computational fluid mechanics, and he's one of the main developers of the DTU software called Ellipsis 3D. He has worked with turbines modeling, parallelization of codes, transition modeling on wind turbine blades, mesh generation, and moving grids. And he will talk about standstill vibrations of wind turbines. So please, Niels.
Okay, thank you, Jakob, for a nice introduction. And you can see my presentation now, I hope.
Yes.
Good. Then I'll start by thanking you for giving me the possibility here to present some work we have done over the last couple of years. And I would like to acknowledge my co-authors here, Christian Grennerslev, Georg Piron, and Ricardo Riva, all DTU staff, and then Sergio Gonzalez Hocas, former DTU colleague and now at CIMNE in Spain. They have all been quite essential for the work I'm going to present here today. The outline for the talk, I'll try and say a few historical things about wind turbine vibrations and standstill. I'll try to characterize what we understand by standstill vibrations. I'll introduce some approaches we have developed and used to analyze vortex-induced vibrations, including some examples, and then I'll try to reach a conclusion. Before going into the real presentation, I want to acknowledge a Danish Innovation Fund project that ran from 20 to 23 called the Prestige, Predicting Wind Turbine Stability in General Inflow, where we work together with a series of partners, Aalborg University, Vestas, LM Wind Power, and Siemens Gamesa, together with DTU, exactly on this topic. This project had 4 technical work packages, one on identifying critical scenarios, one on inflow, and then one on aeroelastic stability of standstill in a general fashion, and then 3 industry tracks where we analyzed specific turbines from the industry participants. So a lot of the work we will see here today was done together with this consortium. And to start on the subject, the movies that we will see here today is not from the Prestige project. They are actually just downloads from LinkedIn to illustrate that this is in fact a real thing. So we see these vibrations also in real life. So standstill vibrations are vibrations of turbines during, you could say, non-productive periods. That could be during erection, before the turbine is connected to the grid, when the turbine is parked during service, for example, or if you shut it down due to production optimization. Then due to wind-induced loads, there is a risk that it will start to vibrate. Often, or in general, this will be connected with flow separation, and it will typically be at relatively high angles of attack, either as stall or as vortex-induced vibrations. The vibrations will be turbine modes, and typically we see that the turbines are vibrating in the first edgewise, or the blades are vibrating in the first edgewise mode, where the aerodynamic damping generally is low. It has a lot to do with the aeroelastic properties of the turbine. The scary part is that it is not necessarily associated with high wind events. So historically, the interest of aeroelastic stability, I guess, a large part of that started with the Tacoma Narrow Bridge and the catastrophic failure. Then it spread to a lot of other topics, vibrations of cylinders in air cooling, airfoil sections for helicopter aerodynamics. And then for wind turbines, some of the first events, at least I'm aware of, is back even before I started doing turbines, and that is back in the 1980, where the Nibe A turbine experienced stall-induced vibrations during operation. Here it was bad airfoil characteristics coupled to the structural pitch or the vibration direction of the blades that caused problems. Then later on in the late 90s, there was quite some research in flutter instability of turbines connected to high tip speeds and lowering torsional stiffness. Also, with the growing turbine size, tower vibration became a more and more widespread phenomena. And I guess that was really no secret in the industry that we saw these things during erection of turbines. Then early 2000, we started to see the first discussions on stall-induced vibration during standstill. And we did at DTU some investigations in 2002 on aeroelastic modeling of stall-induced vibrations. It was also investigated in a European project, the Avatar project, around 2010. And then here at DTU, we slowly started also to look at vortex-induced vibrations around the same time. So the appearance of standstill vibrations that were observed in the early 2000s, to my knowledge, it was first observed in the aeroelastic codes, where people saw high vibrations during standstill. And there was a lot of discussion whether it was an artifact or whether it was a real thing. It was typically experienced when you had high wind speeds, you were operating at angles of attack around CLmax or above. And it showed in the aeroelastic codes that it depended largely on, or heavily on the static airfoil polars. It depended on the dynamic stall modeling. And there wasn't really that much available data on it at that time, at least. And it was also at least speculated that the radial independence of most aeroelastic codes using BEM, where you switch off all induction model, would not necessarily be very well suited to analyze these things. And around the same time, we started to look into vortex-induced vibrations of standstill. And that was based on CFD in order to get rid of the limitation of engineering aerodynamics. So coupling CFD with an aeroelastic or an elastic code to have fluid structure interaction. but also looking into what we call forced motion, so simply forcing the blade or the rotor to vibrate in a given mode shape. We focused a lot on the vortex-induced phenomena, and that was partially due to the belief, and I think I still agree on that assumption, that deep stall is easier to predict with the CFD method than the onset of stall. Therefore, we expect that we have less problems capturing the right physics if we stay in deep stall. The other interesting thing is that the vortex-induced vibrations, in contrast to the stall-induced vibrations, can happen down to potentially very low wind speeds. And at that time, we were lucky to have the possibility of assembling this nice consortium around the standstill problem, and had the prestige project to run these activities. And if you look at standstill vibrations, there are a lot of parameters that you need to take into account. First of all, it is important to be aware that these vibrations are turbine modes. So we will need to know something about the possible mode shapes, the possible frequencies. We will need to have a good idea about the structural damping that potentially could prevent these problems from developing. The actual geometry of the rotor, the chord, the twist, the pre-bend, sweep of blades, the rotor tilt, the rotor cone, all will have a role in where to look for these vibrations. The yaw position, so controlling how the wind hits the parked blades, the pitch setting of the blades, and of course also the rotor azimuth position, whether you have a blade pointing directly into the wind, whether you have a slant angle between the blade and the incoming wind. So there's a lot of parameters that you need to be aware of, and that also makes the design space or the operational envelope you need to investigate quite big. Besides the turbine characteristics, of course, also the inflow is important. The inflow velocity profile, the turning of the wind, so the wind veer is important. We have seen that the time history of the wind can be a potential trigger of these events. Inflow turbulence can either be damping the event by decorrelating things, or it can be the trigger of events due to a turbulent gust. And the temperature in form of density variation will change the load level in the standstill situation. And one of the things we have learned during these years is that if you look at standstill vibrations, the natural buildup of the vibrations are quite slow due to the huge inertia of large-scale rotor blades. So often, to get things going within the window where conditions are favorable for vibrations, you would have to have a igniting event, for example, a yaw repositioning, a pitch motion, a turbulent gust, or some event making the blades have a small vibration that eventually will develop into a critical vibration for the turbine. And at the end, the thing that really controls whether this is going to happen or not is the detailed blade flow characteristics. So whether the flow will, or the situation will develop into a critical vibration situation is very depending on the detailed flow around the blades. And as seen here in the figure, for most standstill situations, I guess for nearly all that are relevant, the 3 rotor blades of a 3-bladed rotor will see very different flow conditions. Here we see a situation where the flow is coming from left to right over a parked rotor that is 90-degree pitch to feather. And you can see that the flow pattern around each blade is very different. The trick is then whether the aerodynamics will do a positive work on the structure, what we often call power injection, so that it pumps energy into the structure and the vibrations will develop and the vibration will be larger and larger. We are still convinced that you can characterize this by some Strohal relation. The problematic part is that with the tapered blades and all the angles that goes into the geometry of this, it's very difficult to predict which airfoil section along the blade is the one that will dictate the critical conditions. And one of the things we have been looking quite some into is how along the span here, from the root to the tip, we see the power injected by the aerodynamics into the blade geometry. So we can see that in some regions of the blade here around 30 meters, there is extraction of energy. Then we have a huge region where all methods predicts positive power injection, then nearly zero at 80 meters, and then again at the tip, there is positive power injection in the situation we are dealing with here. So it is an extremely complicated phenomenon, and there are many possible situations where it can arise. But as said early on, it is a turbine phenomenon, and it will, what we will see is that it will vibrate in turbine modes, and the typical critical ones we see is the 3 edgewise mode, the yaw mode, where the turbine is vibrating around a vertical line in a yaw-like pattern. The tilt mode, where it's tilting around the nacelle, and then a symmetric mode where all blades are in phase, all vibrating in the edgewise direction. And using simple or linearized modal description, we can also predict blade tip amplitude radios. So if I position a rotor with one blade along the at 30 degrees azimuth and having 120 degrees between the blades, I can give an expression, or I know the ratio between the amplitudes of the 3 blades. And that is an advantage later on when we are discussing forced motion. We can also, based on these methods, directly extract from a structural model of a turbine the damping coefficient for a given vibration. Often when we discuss these things, we discuss it in a blade perspective, and then we characterize the flow by 2 angles. One angle that we call the inclination angle, which is basically the angle between the incoming wind and the blade axis. And we have it positive when the flow comes from the tip of the blade towards the root, and negative in the other case. And then we talk about angle of attack, which is very standard. the flow has 0-degree angle of attack when the flow is from leading edge to trailing edge. It is 90-degree when we have the flow towards the pressure side, and then it's 180 when we have the flow from the trailing edge towards the leading edge. So that is typically a parameter we use to characterize what the blades see with respect to flow angles. During the Prestige project, we developed a series of different methods that we could use to analyze these vortex-induced vibrations. Some of them can also be used for the stall-induced. And the first of them is forced motion CFD simulation. So we take a single blade, for example, and vibrate it in a mode shape and according to a frequency, and then monitor what kind of power injection or how much work or power is going into the rotor. The next option is to use a full coupled aerodynamic model coupled to a structural model in the form of an fluid structure interaction. And we have used that for single blade studies as well, typically a blade section clamped at the root, and that can directly be compared to the forced motion studies. And then finally, we can of course do a full turbine model and then modeling the components, the 3 blades in a CFD solver to provide high fidelity loads on the structural model to investigate whether a specific situation will be vibrating. Before describing in a bit more detail these methods, we tried something simpler also in the Prestige project originally. And I guess to not much surprise, if you are looking for vortex-induced vibrations with a standard engineering aeroelastic code, you will not succeed. Basically, the vortex shedding is not modeled correctly in typical engineering aeroelastic codes, and therefore we can't predict vortex-induced vibrations. We could potentially predict stall-induced vibrations for some cases. We know it is difficult, and for example, flow from the trailing edge is probably not well described in that many aeroelastic codes. And definitely the span-wise coupling along the blade will typically, you will switch off your induction model, and the span-wise sections will only be coupled through the angle of attack, and that will probably not give you the right correlation in the span-wise direction. Another thing that were tried initially was that we tried if we could use CFD on the stiff structure to predict if there were some shedding frequencies that would indicate that the blade could vibrate. And at least for some cases, it was quite obvious not the case. So we could, here is a situation where we placed a blade at 18 meters per second and some specific angles here for the flow. And we can see if we run a fixed blade, you will see nice trailed vorticity, but no shedding from the tip of the blade. As soon as we allow it to be elastic, it starts to vibrate and you see a nice shedding pattern behind it. So in many situations, CFD and stiff structures won't tell you much about what is going on in these vibrating cases. The CFD setup we use is more or less a standard setup that we use for most of these simulations. We run, of course, time true, second order accurate in time, a lot of time steps per period, and a deep convergence in the iterative time stepping. We run some grid sequencing to assure that we are decently grid independent. That is often very difficult to achieve. And we, of course, need some kind of deforming grid algorithm to allow the blade to vibrate. The turbulence modeling is typically some of the scale resolving ones. We have used the improved delayed detach eddy simulation technique. We use a fourth order central scheme in the DES region, and then a third order quick scheme in the RANS region. And we have seen a lot of cases where grid around 25 million points well distributed over the blade is sufficient to give a decently accurate result. The scary part is that it's not always the case. And here is an example where we looked at 4 different scenarios. They were all at a pitch angle or a flow angle of 100-degree angle of attack. And then we had different angles to the blade axis from 30, 40, 50, and 60. And what we typically see is that the lower inclination angle, so that when the flow is nearly perpendicular to the blade, these are extremely difficult to get grid independent. And here we actually ended up with around 2.3 billion grid points, and we still saw variation in the 40-degree inclination case. So it can be quite grid demanding to get very accurate results for some of these situations. The forced motion framework, and I can see I might need to speed up a bit, is based on deriving the mode shape and the frequency from a turbine model. For example, we use our in-house Hawk Step 2 code to do this. We also extract a structural damping that can be expressed as a coefficient and times an amplitude squared. So for a given amplitude, we can compute the structural damping. And then we choose a wind speed, a pitch, and an inclination. And then we run the CFD simulation while we vibrate the blade according to a mode shape at a given amplitude. And then we look whether we have power injection into the structure or whether we extract energy from the structure, and how it compares with the aerodynamic or the structural damping. And that can tell us whether we have a stable or an unstable situation. And we can, of course, also look at how the power injection is distributed along the blades. We have used this approach a lot to do parametric variations, especially angle variation of this inclination angle, how we hit the blade axis and the angle of attack. But also wind speed, of course, is important. And you could run different mode shapes. You could take a mode shape from the yaw mode, the tilt mode, or the symmetric mode, and also vary amplitude. So there's a lot of things you can do with the forced motion method. And one of the things we have used it a lot for, besides mapping where are critical situations we would like to run in a full FSI simulation, which is much more computationally expensive, we have used it to estimate limit cycle amplitudes that we should expect from a given scenario. So if we take a single blade, place it at an inclination and an angle of attack, and then choose a wind speed, we can vibrate it with different amplitudes and then see what kind of power injection do we get at different amplitudes. And we get a complex curve like this. The damping from the structural model is this orange curve. And then we can simply find the points where we have equilibrium between the structural damping and the aerodynamic power. And these will be possible limit cycle oscillations. And we have at least we found it interesting when we saw it for the first time. We can actually see that we can have multiple stable limit cycles. So we could have a stable limit cycle here around 25 centimeters, but if we push it above 0.5 meter, the next stable situation would actually be around 1.3 meter amplitude of the vibration. So that's a interesting feature of these vibrations. If we go to one level up in the modeling, we have the full coupled framework. So here we have a loose coupling between our in-house Ellipsis 3D CFD solver and our Hawk 2 aeroelastic code. So what we do is we take the Hawk 2 code, we take away all the engineering aerodynamics and substitute in the CFD solver for the aerodynamics. So we have a framework where we have a Python program basically taking care of exchanging loads from the CFD side for deflections or generalized deflections from the structural side. And that can of course be used to investigate both clamped single blades. You can have just a single blade on your full turbine structure, or you could have the full three-bladed setup. And we have used that to study single blade vortex induced vibration, comparing it with the forced motion to validate that the forced motion is actually a good representation, and that the forced motion is actually a good representation rely on the fact that at the low wind speeds we see for vortex induced vibrations, the structure is not heavily deflected compared to a non-loaded case. So we see actually that the vibration modes for vortex-induced vibrations are very close to the structural modes, and therefore we can just vibrate things in the structural modes, and that gives a decent representation of the full coupled problem. One of the original works here, Sergio did a huge study mapping 448 situations, varying the inclination angle from 0 to 60 some degrees, and the pitch angle or the angle of attack from 70 to 110, and then having the fluid structure solver running for 45 seconds and monitoring the build-up of the tip deflection or tip amplitude in vibration. And that reveals that there are some specific regions here between 40 and 60 degree inclination and around 85 and around 100 where we see relatively large tip vibrations. It has later proved that this might not be a perfect study, but it provided a lot of input and insight at that time. Today, I'm pretty sure we would run for much longer time. We would probably also include some triggering of the vibrations to be sure that we capture most cases. If you don't trigger the situation, you have the chance that it's damped at very low amplitude. And then if you have the smallest ignition, you would actually see a vibration, but you don't capture it unless you ignite it. And then we try to compare a forced motion situation with a full FSI situation, and we can see that both the FSI, shown in the red circles here, and the forced motion, which shows this power injection as function of amplitude, predict approximately the same possible limit cycles for this specific single blade configuration. Yeah, and then a short example, hopefully, let's see the time, yeah, where we illustrate that it is actually important to look at these problems as rotor problems and not single blade problems. So this is a situation where we have 18 meters per second coming from the side. The rotor is parked 90 degree or 80 degree pitched, and the azimuth of blade 1 is 60 degrees. Then we ignite it for the first 230 seconds to vibrate in the yaw mode, and then we switches this off gradually. So we, after 250 seconds, are in a mode where we drive it with the CFD. If we look at what happens, then we have blade 1 pointing into the wind, we have blade 2 along the tower, and blade 3 pointing, having the tip in the direction of the downgoing wind. And what we see is that after the original forcing here up to 230 seconds, when we let the rotor free to vibrate under the CFD loads, we see a slow development of the tip amplitude for both blade 1 and blade 3, whereas the first blade, the one that, or blade 2 that points along the tower, is nearly not vibrating, and that is typically for a yaw mode. If we want to understand what happens here after 800 seconds, we see a sudden increase in the growth rate of the vibration amplitude until we reach the limit cycle. If we look at the individual blades, blade 2 along the tower is not very active. It's basically not providing any power input until 1000 seconds, and after that it is actually weakly damping for the vibration. The downwind blade, blade 3, is not very active up to the 800 seconds where we saw things started to change. So all the startup of the vibration is driven by the blade that points into the wind, that increases the amplitudes of all 3 blades up to a point where also this blade 3 that points downwind starts to vibrate and put energy into the system. At around 1100 seconds, this downwind blade actually inputs much more energy than the blade that actually started the vibration do, and eventually blade 1 goes down in power input, while blade 3 keeps increasing until 1300 seconds, and then we reach the limit cycle amplitude. So here we see a situation where we go from one blade inputting power to another blade inputting power, and that we would never be able to do just looking at a single blade. So here it is quite essential that we can analyze the full rotor and the full scenario. I think I will skip this one. And this is just a small animation, not of exactly the same situation, but one where the pitch setting is 90 instead of 80. But also here we see quite big amplitudes in the limit cycle oscillation. We also developed a small model based on the similarity between the structural modes and the aeroelastic modes. We can, based on the modal description, derive a small model that can predict the time development of the amplitude when we know something about the aerodynamic power, the structural dissipation due to damping, a damping coefficient that we can extract from the modal model, and the vibration frequency. We have an expression that will simply allow us to predict time histories of the amplitude when we know these amplitude power curves that we saw before. So we can actually in a very simple way, vary different, for example, the starting amplitude, and see how it develops. And we can see that there's quite good agreement also with the full FSI approach. This method can also be generalized. Here it's for a one-bladed situation. It can also be used for a three-bladed situation. Following up on that, where we actually can use the forced motion to predict the time history of the amplitude development, if we go to stall-induced vibrations, then the structural modes and the aeroelastic modes starts to deviate, and then the forced motion approach is probably no longer valid. We can also suspect that traditional engineering codes will have a hard time predicting the correct mean deflection of blades during standstill. So it is complicated if you go from the vortex-induced vibrations, where we know a lot about the mode shapes, to the stall-induced cases where we have higher wind speeds, more deflections, and basically aeroelastic mode shapes. In that situations, the only thing that we can do is maybe to go to the full FSI coupling with the CFD. One of the things which is always nice to have and which is difficult for these cases is the comparison with the experiment. We know that the vibration phenomenon, and we saw it from these LinkedIn videos, it has been documented several times. We know it exists. The problem is to know the turbine data, the actual wind data. So the videos can provide the proof that it exists, but it can really not be used for validation. There are no full-scale data sets available in the open literature. Recently, TNO has presented a campaign from their TIADE experiment where they observed vibrations, but I'm afraid that we will never have the relevant turbine data, and maybe not even the inflow data to reproduce these cases. So it's definitely a thing that we are in need of as a research community, cases for validation, so full turbine model, including the damping, well-characterized inflow, and for example, tip deflection, root moments, and other things. So experimental data is definitely needed for these standstill vibrations. Yes, and to the conclusions, I've tried to introduce some of the findings we have seen in our prestige project around standstill vibrations. I've described in very rough details the approaches we have used, the forced motion single blade approach and the full coupled FSI. And when we started out in the project, we didn't really expect that the forced motion would be very valuable, but we have actually used it a lot and have found great use of it because it is factors faster than a full FSI, and it can bring you to the right point before you actually start to run the even more expensive FSI simulations. And I hope also I managed to bring across the message that these vibrations, they are full turbine vibrations, and it is important to include the full turbine when you investigate these problems. And I believe that is what I plan to say. And
thank you very much, Niels. Thank you for a very interesting presentation. And we have questions. I see one from Jason Junkman. Structural damping is obviously important for the limit cycle response. How did you quantify the structural damping in your case studies?
What we do is that we, through the modal modeling the Hawk-Step 2 and a given turbine model, there you can basically extract this damping coefficient. So you get a very simple expression for a given mode shape. You have a coefficient times the modal amplitude squared that will give you the structural damping. But of course, this damping will not be more correct than what you put into your turbine model. So if your turbine model has the wrong logarithmic decrement, then the damping will of course be off. And that is also why we, for many of the cases we have looked into, run the FSI with basically no structural damping.
Okay.
For the forced motion, it's a lot simpler. There you can compare with different damping coefficients afterwards.
Yeah, so Noah Myron has a comment. Maybe he just says that it could be experimentally quantified as well, but not so easy in practice, I suppose. Yeah.
Thanks. Yeah, that's common practice. This is something I think we tried to explore as an industry 10 to 15 years ago, operational modal analysis, but estimating and quantifying that forcing function on the blades is just it's not easy, but that's definitely a good way to get localized on some of these stiffness changes and things like that, and damping, of course. So just wanted to add that comment.
Yeah, thank you.
Thank you.
And Emmanuel?
Yes, thank you, Niels, for your talk. On one of your slides where you had this growing of the power with the 3 blades, is the interaction between the blades structural as well as aerodynamic? Like, or are they all individually flapping? And also, the question is also like, do you have the full turbine behind the scene in Hawk 2, like the shaft, tilting, and those kind of things?
Yes. There is, of course, we must expect there is some aerodynamic coupling. For the cases we have looked into so far, the aerodynamic coupling between the blades is weak. The main coupling is that you are vibrating in turbine mode. So if your upstream blade is vibrating with a given amplitude in a yaw mode, your downwind blade will follow, and we know the exact amplitude ratio between these two. So the main part of it is actually through the structure, and we have the full turbine model there below the CFD solver. So it is basically the upstream blade driving the vibrations up to a point where the downstream blade also suddenly have positive power injection. So it's really a nasty case.
Sounds good. Thanks. If I can have a small follow-up on the same plot that I'm talking about, you had 2 lines. You had the Hawk 2 that was dashed, and you had CFD that was plain. I'm not sure I captured what was the difference between the two.
Now I can try and see if
You
I
have
can
to
bring
share
it up.
again. Then. Yeah, good.
See if I can.
Yes, this one.
Yes, this figure is taken from somewhere else, and we do determine the power injection in 2 ways, based on the Hawk 2 output and directly from the CFD output, and preferably they should be totally identical, and they are close, not perfect, but close. Should I just leave it up, Jakob, or?
Yeah, you want to do that. More questions, please? Well, I have one. I was wondering about when is this most relevant? You said something about under construction or installation, and also stand still during normal operation. But I guess in normal operation, when the turbine is not running, then it yaws, so it faces the wind all the time, and then I assume it's not a problem. So what cases are the most relevant?
The regions where we hear a lot of fear from manufacturers are during erection, for example. If you
Okay.
have 1, 2, 3 blades on the turbine and it's not grid connected, then you're really bad off. And often you wouldn't, even if you had power on, be allowed to yaw the turbine if there's a crane close to the turbine. So that is a really bad situation. Another case could be if you have a grid problem, so you're not connected to power and can't position your turbine.
All right. In the first case, steel chimneys, they have these spiral things on them to prevent this. Could you imagine something similar here, that you could put those under installation and then take them off when you start the turbine? Or
These are things that I guess our industry partners prefer not to discuss with us. But we know that people have tried many things, fish nets and other things. Everything comes with a cost. So you could say if you can position your turbine in a situation where you know the risk is small, it's preferable. If you pull off half of the vortex generators when you erect the turbine, it's a bad case.
Yeah. All right. Good. Any more questions? Anyone? Okay. Doesn't seem to be the case. But then again, I'd like to thank Niels for his very interesting presentation and good answers to all the questions. And I would say that if you have ideas for new presentations, then please come forward either to me or Sue Ellen, and we will make you a slot available for you in this seminar series. So thank you very much.
Thank you, Jakob. And definitely, if people have questions that they didn't think of now, please contact me, and we will be very willing to discuss with people. So thank you very much for listening.
Okay. Yeah. Bye-bye.
Goodbye.
Goodbye.